Hello everyone, my name is Umid Khan. In this presentation I will discuss about closed loop system. First comes S-plane. What is S-plane? The S-plane is the complex plane on which Laplace transforms are graphed. Next is what is stability. The stability of a control system is defined as the ability of any system to provide a bounded output when a bounded input is given. So if I give a bounded input and I get a bounded output, I may call the system as a stable system. Here we can see the S-plane and relation between S-plane and stability. So S-plane is basically, as we know, S equals to sigma plus j omega. So when the location of poles falls on the left hand side of the S-plane, the system is called stable system. And when the poles are on the right hand side of the S-plane, the system is called unstable system. And when the poles are on the j omega axis of the S-plane, the system is called critically stable system. Now what is unstable system? Systems which have at least one pole in the right hand side of S-plane is called unstable system. And what is stable system? Systems which have all poles in the left hand side of the S-plane is called stable system. Marginally stable systems are systems which have poles on the imaginary axis of the S-plane. And what is conditionally stable system? These are the systems which have poles on the right hand side of S-plane, but which can be made stable by increasing the gain. Now what is absolute stability? Absolute stability means whether system is stable or unstable. And what is relative stability? Relative stability gives the degree of stability or how close it is to instability. Next is Routh-Hurwitz criteria. The Routh-Hurwitz criteria states that any system can be stable if and only if all the roots of the first column have the same sign, and if it does not has the same sign or there is a sign change, then the number of sign changes in the first column is equal to the number of roots of the characteristics equation in the right half of the S-plane, that is equals to the number of the roots with positive real parts. Next comes what are the advantages of Routh-Hurwitz criteria. Here we can find the stability of the system without solving the equation. We can easily determine the relative stability of the system. By this method we can determine the range of K for stability. But there are also some limitations of Routh-Hurwitz criteria. That is, this criteria is applicable only for linear system. It does not provide the exact location of poles on the right hand and left half of the S-plane. In case of the characteristics equation, it is valid only for real coefficients. Now this is Routh-Hardwick criteria. So we are considering the following characteristics. Polynomial is a0 is to the power n plus a1 is to the power n minus 1 plus so on, and plus a to n equals to 0. So at first we have to arrange the coefficients of the above equation in two rows. So row 1 is a0, a2, a4, a6 and so on, and row 2 is a1, a3, a5, a7 and so on. From these two rows we will form the third row. In row 3 we get b1, b3 and b5, where b1 equals to minus a0, a3 minus a1, a2 divided by a1. And similarly we get the formula of b3, that is minus a0, a5 minus a1, a5 divided by a1. Similarly, now we shall form fourth row by using second and third row. The fourth row is c1, c3 and c5, where c1 equals to minus a1, b3 minus b1, a3 divided by b1, and c3 equals to minus a1, b5 minus b1, a5 whole divided by b1. Then we shall continue this procedure for forming a new rows. Here is a problem on Routh-Hardwick criteria. Here we have to check the stability of the system whose characteristics equation is s to the power 4 plus 2s cube plus 6s square plus 4s plus 1 equals to 0. At first we have to obtain the area of coefficients. The coefficient of s to the power 4 is 161, that of s cube is 2, 4, and we have to find the coefficients of s square. So the first coefficient of s square is b1. Suppose by using the formula we get b1 equals to 4, and then we get c1, that is equals to 3.5, b2 equals to 1 and d1 equals to 1 by using the formula we have discussed in the previous slide. As we can see that all the coefficients in the first column are of same sign, so the given equation has no roots with positive real parts. So therefore the system is said to be stable. There is also another example of Routh-Hardwick criteria. In this problem we can see that there is a sign change in the first column. Basically there is two changes in sign which appears in the first column. As we can see that from plus 1 it changes to minus 22, and from minus 22 it changes to plus 24. So there are two sign changes in the first column. So the two roots of the characteristics equation lie on the right hand side of the S-plane. So the system is unstable. Next is Nyquist stability criteria. The Nyquist stability criteria works on the principle of argument. It states that if there are p poles and z zeros are enclosed by the S-plane closed path, then the corresponding GSHS plane must encircle the origin pz times. So we can write the number of encirclement a n as n equals to p minus z. We know that the open loop control system is stable if there is no open loop pole in the right hand half of the S-plane. So P equals to 0, so n becomes n equals to minus z. And for closed loop control, the system is stable if there is no closed loop pole in the right hand side of the S-plane. So it is z equals to 0, so n is equal to P. The Nyquist stability criteria states that the number of encirclements about the critical point 1 plus J0 must be equal to the poles of characteristics equation, which is nothing but the poles of the open loop transfer function in the right half of the S-plane. The shift of in the origin to 1 plus J0 gives the characteristics equation plane. Thank you all for watching and listening to this presentation.